A paintball marker, also known as a paintball gun, paint gun, or marker, is the main piece of paintball equipment in the sport of paintball. Markers use an expanding gas, such as carbon dioxide, CO2, or compressed air, to propel paintballs through the barrel and quickly strike a target. The term marker is derived from its original use as a means for forestry personnel to mark trees and ranchers to mark wandering cattle. The muzzle velocity of paintball markers is approximately 90 m/s, 300 feet/s. While greater muzzle velocity is possible, it has been ruled unsafe for use on most commercial paintball fields. When paintballs hit an object at high speed, they have the potential to cause damage. A paintball colliding with human skin, even protected by cloth, may cause bruising or further tissue damage. However, the damage depends on the paintball's velocity, its impact angle, whether it breaks, and which part of the body it hits. Because of the potential for serious soft tissue damage, paintball players must wear masks to protect their eyes, mouth, and ears when barrel-blocking devices are not preventing paintball markers from firing. Most paintball markers can be disassembled into four main components: the body, hopper, barrel, and gas system or air tank. Marker types. Paintball markers fall into two main categories in terms of mechanism: mechanical and electropneumatic. Mechanically operated. Mechanically operated paintball markers operate using solely mechanical means, and as such do not use electropneumatic solenoids controlled by an electronic board to fire. There are five main methods of mechanical operation. Pump or bolt action. The mechanism of the marker must be manually reset in between each shot, similar to pump action shotguns and bolt action rifles. Markers of this type are the oldest used in the sport, as the first ever game of paintball was played using the bolt action Nelspot pistol. There are two main patterns of internals upon which most pump and bolt action markers operate. Sheridan valve, named after the Sheridan series of markers which first employed this design. Markers which employ this mechanism have the bolt which loads the paintball is located in a separate tube from the hammer and valve. To cock the mechanism, the bolt is pulled backwards, thus opening the breech and loading a paintball. Doing so also pulls the hammer backwards against the main spring, which is then held back by a sear connected to the trigger. The bolt is then pushed forward, which loads the paintball into the barrel, and the marker is ready to fire. Pulling the trigger releases the hammer, which is propelled forward by the main spring, hitting the valve pin and opening the valve, which allows compressed gas to flow from the valve chamber into the barrel chamber, thus propelling the loaded paintball forward and out of the barrel. The valve spring then closes the valve with the hammer still resting on the valve pin, after which this cycle must be repaired in order to fire another paintball. Notable examples of markers which operate in this way include the Sheridan K2, the War Games Products Sniper, and the Chipley Custom Machine S6. Nelson valve, named after the Nelson Paint Company, whose marker, the Nelspot 007, first employed this mechanism. In such markers, the bolt, hammer and valve are all located in the same tube. To cock the mechanism, the bolt is pulled back against the main spring to allow a paintball to fall into the breech, at which point the sear latches the hammer to the bolt with the compressed main spring in between them. The bolt and attached hammer are then pushed forward to close the breech and load the paintball into the barrel, at which point the sear can be engaged by the trigger and the marker is ready to fire. Pulling the trigger disengages the sear from the bolt, allowing the main spring to propel the hammer rearwards onto the power tube, thus opening the valve and allowing compressed gases to flow from the valve chamber to the barrel through the power tube and bolt, which propel the loaded paintball forward. The valve is then closed by the valve spring and the marker is ready to be recocked for the next shot. Notable examples of markers which employ this mechanism are the Nelson Nelspot 007, the CCI Phantom, and the Redux. Stirling hybrid valve, a variation or hybrid of these two methods of operation, has been employed in the design of the Aero Precision Stirling, wherein the bolt is located in a separate tube, as in a Sheridan valved marker. The hammer latches to a carrier similar to how it would to the bolt in a Nelson valve design, and when released it hits a Sheridan-styled pin valve. There is significant debate as to what type of operations the Stirling employs, as some consider it to be a hybrid between the two main designs, and others simply consider it to be a stacked tube Nelson. Double action. the trigger mechanism of the marker both fires and resets the firing mechanism, similar to the way a double-action revolver operates. Examples include the Line SI Advantage, the NSG Splat Master Repeat and the Brass Eagle Barracuda. Throwback semi-auto, the mechanism of the marker is cycled using gases released by the valve which reset the firing mechanism between each shot, similar to the way some semi-automatic rifles such as the AK-47 operates. The internals of blowback-operated markers can be either inline, with the bolt, valve, and hammer all aligned along the same axis such as the Tipman 98, or stacked tube with the bolt in a separate tube from the hammer and valve such as the Kingman Spider. Blow-forward semi-auto, the firing mechanism of the marker operates using the gases stored in the valve to cycle the bolt and fire the paintball, after which a spring resets the mechanism for the next shot. Notable examples include the Airgun Designs Automag, Tipman X7 Phenom and the Tiberius Arms T8. Pneumatically operated semi-auto, a low-pressure pneumatic piston controlled by a four-way valve connected to the trigger resets the firing mechanism in between shots, and can be thought of as semi-auto conversions of markers which would otherwise be pump or bolt action. Notable examples include the WGP Autococker, the Palmer's Pursuit Shop Blazer and Typhoon. Electro-pneumatically operated. In electromagnetic designs, the trigger, instead of being mechanically linked to the action of the marker, simply activates an electronic microswitch, or more recently, a magnetic or optical sensor. That information is passed through control circuitry to a computer-controlled solenoid valve which can open and close very quickly and precisely, allowing gas to move into or out of various pressure chambers in the marker to move the bolt and fire the paintball. This disconnect of the trigger from the action allows electronic trigger pulls to be very short in length and very lightweight, similar to a mouse click. The mechanisms are virtually identical, which dramatically increases rate of fire over a fully mechanical design. Solenoid-controlled gas valve designs also allow for reduced weight of internal parts, which both lightens overall weight and reduces the time it takes for the marker to cycle through firing a single paintball. Each branch favors a different aesthetic and values different aspects of marker design. Marker body. Most of the marker's functions and aesthetic features are contained in its body, which contains the main components of the firing mechanism, the trigger frame, bolt, and valve. Most paintball marker bodies are constructed from aluminium to reduce the marker's weight, and feature custom milling and color anodizing. External design. The largest external and ergonomic difference in marker bodies is in the trigger and barrel position. Designers of expensive models attempt to position the trigger frame forward towards the center, or slightly forward of center of the body on speedball-oriented markers. This allows the HPA tank to be mounted in a position allowing compactness and balance without requiring any additional modifications that allow the tank to fall down and forwards. Such aftermarket drop forwards may create a larger gun profile, which can result in eliminations due to hopper hits. Users often modify less expensive markers to allow a similar mode of operation, albeit by sacrificing a low profile. Although this is not important in games where equipment hits are not counted, in most games, including woods ball games, hopper hits are counted as an elimination. Some markers mount the barrel farther back in the gun body to preserve a compact design, sacrificing the positioning of the trigger forward on the marker body. Paintball markers are also categorized to a lesser extent by which play style of paintball in which they are intended for use: sporting paintball such as speedball and stock class paintball, or military simulation style games such as woods ball. Trigger frame. Triggers are the player's primary means of interacting with the marker. The amount of force required to fire the marker, as well as the distance the trigger travels before actuating, called the throw, has a marked effect upon the player's ability to achieve high rates of fire. Many markers, especially higher-priced markers, use electronic trigger frames with a variety of sensing methods, including microswitches, Hall effect sensors or break beam infrared switches. These triggers have short throws, allowing a high rate of fire. Non-electronic markers sometimes use carefully set pneumatic to achieve a light and short trigger pull. The trigger frame on non-electronic mechanical markers simply use a series of springs and levers to drop a sear, which propels the hammer in the body forward. On electronic markers, the trigger frame houses the electronics that control the solenoid, as well as features such as ball detection systems. Upgraded circuit boards that add improved features are available. Bolt and valve assembly. The bolt and valve assembly is the mechanism which fires the marker. The valve is a mechanical switch that controls whether or not the marker is firing. The bolt directs the flow of air and controls the entry of paintballs into the chamber. The bolt and valve may be separate components, as in many blowback and poppet-based electromagnetic markers. Alternatively, the valve may be built into the bolt, as in spool valve electromagnetic markers. Most modern markers have an open bolt design. When the marker is at rest, the bolt is in the back position, and the firing chamber is exposed to the stack of paintballs being fed by the loader. Some markers have closed bolt designs. In the rest position, the bolt and paintball to be fired are forward and the feed stack is closed off from the chamber. Closed bolt markers were thought to be more accurate because there is no reciprocating mass when the marker is fired. However, tests have shown that the position of the bolt has little effect on a marker's accuracy. Bolt and valve in mechanical markers. The majority of mechanical markers employ a simple blowback design utilizing a poppet valve, also known as a pin valve, which is opened when struck by a compression force, provided in the form of a hammer propelled by a spring. This type of marker generally uses a stacked tube design, in which the valve and hammer is contained in the lower tube, while the bolt, which is connected to the hammer, is in the upper tube. When the hammer is pulled backwards, the internal spring compresses, exerting exponential pressure against the hammer's continued backwards motion. As the hammer and spring mechanism reaches the far end of its backwards range of travel, it is caught and locked in place by a metal catching device known as the sear. The sear holds the hammer in place, allowing the kinetic energy of the bolt's forward motion to be released whenever the sear is depressed. As the trigger is pulled, the sear becomes depressed and allows the hammer to be propelled forward by the spring. The hammer collides with the valve, releasing gas from the external pressurized tank into the internal bolt chamber. The ensuing burst of gas channels out the front end of the bolt, propelling the paintball down the barrel. The rest of the gas pushes backwards on the hammer, pushing both it and the bolt backwards until the mechanism is once again caught on the sear. Once caught, the hammer is ready to repeat the blowback process. In cases where the pressure from the storage vessel drops under the minimum required to complete the action cycle, the marker may run away firing rapidly without additional trigger pulls required. Poppet valves are easy to replace and require little maintenance. The downside to this design, however, is its high operating pressure, which leads to a larger recoil and less accuracy. Some markers have a separate firing and recocking sequence, which decreases the recoil caused by the cycling of the hammer. Markers with a hammer have a firing delay when compared to a full electropneumatic. Some markers are a hybrid of mechanical and electronic features. In these markers, the hammer and spring continues to activate the valve, but the hammer is released by a solenoid in an electronic trigger frame. Bolt and valve in electropneumatic markers. Instead of the spring and hammer used to actuate the valve and cycle the bolt assembly in mechanical markers, electropneumatic markers use the rerouting of air to different locations in the marker. This rerouting is controlled by a solenoid that is activated by the trigger. The two types of bolt and valve mechanisms in electropneumatic markers are the poppet valve and spool valve. Poppet valve-based electropneumatic markers are very similar to mechanical blowback markers. These pave a stacked tube construction, built around a poppet valve, that is opened when struck by a force. Whereas mechanical markers provide that force with a hammer propelled by a spring, the valve in poppet valve markers are activated by a pneumatic ram. The bolt is connected to the ram. Poppet valve markers have several disadvantages when compared to spool valves: external moving parts, higher pines sure required for poppet to seal, a reciprocating mass and a louder firing signature. However, they are also generally more gas efficient than spool valve models because the poppet valve opens rapidly and dips air into the firing chamber faster. Examples of markers that utilize this mechanism are the WDP Angel, Planet Eclipse Ego, Bob Long Intimidator, and Bushmaster. In spool valve-based electropneumatic markers, the bolt also acts as the valve. This eliminates the need for a stacked tube construction. Spool valve markers have a more compact profile. Instead of a cycling hammer or ram that strikes a pin valve, the movement of the bolt is controlled by the routing of air into small chambers in front of or behind the bolt. An air reservoir behind the bolt contains the air that is to fire the paintball. When the marker is at rest, air is routed to the front of the bolt to prevent the air in the reservoir from escaping. In an unbalanced spool valve design, when the trigger is pulled, that air is exhausted from the marker, allowing the air in the reservoir to push the bolt forwards. In a balanced spool valve design, the air in the reservoir cannot force the bolt open. Instead, the air from the front of the bolt is rerouted to a small chamber behind the bolt, separate from the reservoir, which then pushes the bolt forward. In either case, the movement of the bolt forward exposes pathways in the bolt or the marker that allow the air in the reservoir behind the bolt to surge forward and fire the paintball. Afterwards, airflow to the front of the bolt is restored, pushing the bolt back into its resting position. A typical spool valve has at least one O-ring that undergoes a shear and compression duty cycle for every shot, leading to faster wear and less reliability. Additionally, smaller valve openings and longer opening times makes them less gas efficient than their poppet valve counterparts. Since spool valve markers have reduced reciprocating mass, and can be operated at lower pressures, they have less recoil and a reduced sound signature. Examples of markers that utilize this mechanism are the dye matrix, Smart Parts Shocker, Smart Parts Ion, and the MacDev clone. Tuning the bolt and valve system. In mechanical and poppet-based electropneumatic markers, the valve is usually designed to accommodate a specific operating pressure. Low-pressure valves provide quieter operation and increased gas efficiency when tuned properly. However, excessively low pressure can decrease gas efficiency as dramatically as excessively high pressure. Additionally, the valve must be set to release enough air to fire the paintball. If the valve is not tuned properly, insufficient air to fire the paintball may reach the bolt. This phenomenon, known as shoot-down, causes fired paintballs to gradually lose range, and can also occur at high rates of fire. Some markers have integral or external chambers, called low-pressure chambers, which hold a large volume of gas behind the valve to prevent shoot-down. Tuning can also prevent air blowing up the feed tube upon firing, which disrupts the feeding of paintballs into the marker. Loaders. Loaders, commonly known as hoppers, hold paintballs for the marker to fire. The main types are gravity feed, agitating and force feed. Stick feeds are also used to hold paintballs, although they are not considered to be hoppers. While agitating and force feed hoppers facilitate a higher rate of fire, they are subject to battery failure, as well as degradation if they come into contact with moisture. Such hoppers which are not fitted with photoreceptors are prone to problems with ball breaks. When a paintball leaks paint into the hopper from a break in the hopper, the gelatin shells of the paintballs can deteriorate, causing them to stick together as well as jam in the barrel. Stick feed. Stick feeds are mainly used on pump and stock class markers. They consist of simple tubes that hold between 10 and 20 paintballs. Stick feeds are usually parallel to the barrel. Player must tip the marker to load the next paintball. Some stick feeds are vertical, or at an incline to facilitate gravity feeding, though this contravenes accepted stock class guidelines. Gravity feed. Gravity feed is the simplest and cheapest form of hopper available. Gravity feed hoppers consist of a large container and a feed tube molded into the bottom. Paintballs roll down the sloped sides, through the tube and into the marker. These hoppers have a maximum rate of 11.6 balls per second. Gravity feed hoppers are very cheap, since they are made of only a shell and a lid, but can become jammed easily as paintballs accumulate above the tube. Rocking the marker, and hopper, occasionally can prevent the paintballs from jamming in the hopper. This problem is exacerbated when using a fully electronic marker. Most mechanical markers use a blowback system for recocking, or other methods where a large reciprocating mass is involved. This will shake the balls in the hopper slightly, facilitating gravity feed. A marker with both electronically controlled recocking and firing may exhibit no shake whatsoever while operating. Because of this, small packs in the hopper are not broken up and feeding problems result. There are also loaders that resemble military sights that mimic an ACOG or a red dot sight, with 20 paintballs capacity at 10 balls per second. Used normally in milsim events or low capacity, low cap, events, for e.g., each player can use a maximum of 50 paintballs. Agitating. Agitating hoppers use a propeller, spinning inside the container, to agitate the paintballs. This prevents them from jamming at the feed neck, allowing them to feed more rapidly than gravity feeds. Older tournament-level hoppers are of the agitating type, since the higher rate of fire requires a reliable hopper. There are two types of agitating hoppers, those with sensors called eyes and those without. The eyes consist of a LED, light-emitting diode, and a photodetector, typically a phototransistor or photodiode, inside the neck or tube of the hopper, to detect the presence of a ball. In a hopper, the eyes detect when a ball is absent, causing it to turn. Agitating hoppers without eyes will quickly deplete batteries and may bend or dent paintballs, causing a short, less air-efficient, skew shot. Agitating hoppers with eyes will only spin in the absence of a ball, preventing damage and prolonging battery life. A third type of agitating hopper, the cyclone feed system manufactured by Tipman, reroutes gas to agitate the feeding mechanism. It does not need batteries to operate. Force feed. Force feed hoppers use an impeller to capture paintballs and force them into the marker. The impeller is either spring-loaded or powered by a belt system, allowing it to maintain constant pressure on the stack of paintballs in the feed tube. This allows force feed hoppers to feed paintballs at a rate exceeding 50 balls per second, since the mechanism does not rely on gravity. Force feed hoppers are the dominant type used in tournaments, being the only type of loader capable of maintaining the high rate of fire of electropneumatic markers. Some markers use force-fed loaders shaped as firearms magazines. These are preferred when a low profile is required, as in woods ball sniper positions. Even more unusual are fully contained magazines, incorporating both a source of propellant gas and force-fed paintballs. The newest type of force-feed hoppers communicate wirelessly with the marker's electronics using radio frequency. This allows the hopper to begin feeding paintballs before the pneumatic system of the marker has begun cycling the next shot. This system almost totally eliminates misfeeds and can increase the speed of the loader and the battery life because the loader is only in operation when the marker is preparing to fire. Propellant system. The tank holds compressed gas, which is used to propel the paintballs through the marker barrel. The tank is usually filled with carbon dioxide or compressed air. High-pressure air, HPA, is also known as nitrogen, as air is 78% nitrogen, or because these systems can be filled with industrial nitrogen. Due to the instabilities of carbon dioxide, HPA tanks are required for consistent velocity. Other propulsion methods include the combustion of small quantities of propane or electromechanically operated spring plunger combinations similar to that used in an airsoft gun. Carbon dioxide. Carbon dioxide, CO2, is a propellant used in paintball, especially in inexpensive markers. It is usually available in a 12-gram powerlet, mainly used in stock paintball and in paintball pistols, or a tank. The capacity of a carbon dioxide tank is measured in ounces of liquid and it is filled with liquid CO2. At room temperatures the vapor pressure is about 5,500 kilopascals, 800 psi. The CO2 liquid must vaporize into a gas before it can be used. This causes problems such as inconsistent velocity. Cold weather can cause problems with this system, reducing the vapor pressure and increasing the chance for liquefied gas to be drawn into the marker. The low-temperature liquid can damage the internal mechanisms. Anti-siphon tanks have a tube inside the cylinder, which is bent to prevent liquid carbon dioxide from being drawn into the gun. On the other hand, a number of paint guns were designed with specific valves to operate on liquid CO2, including some early Tipman models and the Mega Z from Montnil, thus solving the problem caused by phase changes. Siphon-equipped CO2 tanks are easily identified by the clunking sound their weight makes when the tank is tipped. After many years of use, carbon dioxide has almost been universally replaced with high-pressure air systems, see below. High-pressure air. High-pressure air, compressed air, or nitrogen, is stored in the tank at a very high pressure, typically 21,000-31,000 kPa, 3,004,500 psi. Output is controlled with an attached regulator, regulating the pressure between 1,700 kPa, 250 psi, and 5,900 kPa, 860 psi, depending on the type of tank. The advantage of using regulated HPA over carbon dioxide, CO2, is pressure consistency and temperature stability, where CO2 reacts to temperature changes, causing inaccuracy and freezing during heavy use. The most popular tank size is 1,100 cubic centimeters, 67 cu in, at 31,000 kPa, 4,500 psi, providing 800-1100 shots. HPA tanks are more expensive because they must accommodate very high pressures. They are manufactured as steel, aluminium, or wrapped carbon fiber tanks, the latter being the most expensive and most lightweight. Most players with electronic markers use HPA because if CO2 is used, the marker's electronic solenoid valve can be damaged if liquid CO2 enters it. Users are warned not put any type of lubricant in the fill nipple port of a HPA tank, as petroleum may burn when subjected to highly compressed air, causing an explosion, like in a diesel engine. Propane. A far less common propellant is propane, featured only in the Tipman C3. Rather than simply releasing gas as in high-pressure air and CO2 markers, the propane is ignited in a combustion chamber, increasing pressure and opening a valve that lets the expanding gas propel the paintball. There are a number of advantages, mainly shots per tank, ranging from 30,000 to 50,000 shots, depending on the size of the tank, as opposed to the typical 1,000 to 2,000 shots that are standard with high-pressure air or CO2 tanks. Another advantage includes availability, as propane is readily available in many stores, whereas CO2 and high-pressure air are most commonly filled from compressors or pre-filled tanks, which are less common. It can also be considered safer too, because a typical high-pressure air tank holds air at 21,000-31,000 kPa, 3,004,500 psi, and a CO2 tank at 5,500 kPa, 800 psi, but propane is stored at 2,100 kPa, 300 psi. However, propane produces heat, which, when firing for an extended period at high rates of fire, can cause burns if improperly handled. It can also be a fire hazard. The Tipman C3 releases small amounts of flames from the vents in the combustion chamber and out of the barrel when firing. If a marker develops a leak from improper maintenance, it could cause a fire. Gas regulation. Marker systems have a variety of regulator configurations, ranging from completely unregulated to high-end systems using 4 regulators, some with multiple stages. The regulator system affects both the accuracy and the firing velocity. Carbon dioxide regulators must also prevent liquid gas from entering the marker and expanding, causing a dangerous surge in velocity. Regulators used with carbon dioxide often sacrifice throughput and accuracy to ensure the marker operates safely. HPA-only regulators tend to have an extremely high throughput and are designed to ensure uniform pressure between shots to ensure marker accuracy at high rates of fire. Tournament markers usually are equipped with 2 regulators, and another on the tank, each with a specific function. The tank regulator decreases the pressure of air from 21,000-31,000 kPa, 3,004,500 psi, to 4,105,500 kPa, 5,9,800 psi. A second regulator is used to further reduce this pressure to near the firing pressure. This reduction allows for greater consistency. The air is then supplied to a regulator on the marker body, where the final output pressure is selected. This can be between 5,500 kPa, 800 psi, for entirely unregulated carbon dioxide markers to approximately 1000 kPa, 150 psi, for extremely low pressure markers. After the firing pressure is decided, tournament-oriented markers use another regulator to supply gas to a separate pneumatic system, to power any other functions, such as bolt movement. This is an extremely low volume, extremely low pressure regulator, usually under 690 kPa, 100 psi. Barrels. The marker's barrel directs the paintball and controls the release of the gas pocket behind it. Several different bore sizes are made, to fit different sizes of paintball, and there are many lengths and styles. Most modern paintball markers have barrels that screw into the front receiver. Older types slide the barrel on and screw it in place. Barrel threading must be matched to that of the marker. Common threads are Angel, Autococker, Impulse/Ion, Shocker, Spider, A5, and 98 Custom. Barrels are manufactured in 3 basic configurations: 1-piece, 2-piece, and 3-piece. A barrel with interchangeable bores, with either 2 or 3-piece, is called a barrel system, rather than a 2-piece or 3-piece barrel. This prevents confusion, as many 2-piece barrel systems do not use an interchangeable bore system. 1-piece barrels are machined from a single piece of material, usually aluminium, but stainless steel has historically been popular. Paintballs can range from .50 to .695 caliber, 12.70 to 17.65 mm, and barrels are made to match these diameters. Some 1-piece barrels have a stepped bore that increases from their rated bore size to around .70 caliber, 17.78 mm, after 8 inches, 200 mm. 1-piece barrels are generally less expensive to produce and therefore to purchase, but if a different bore size is desired, for a closer fit to the size of a given brand or batch of paintballs, an entirely new barrel is required. The use of a single material for the entire barrel means that disadvantages of certain materials, such as durability, aluminum, or weight, stainless steel, cannot be mitigated. 2-piece barrels consist of a front and B.
Please subscribe and thanks for watching.